On the topic of Laplace transformation, let us begin by a short introduction. As you remember in elementary calculus, you learned that differentiation and integration as different operations are transforms. It means that, roughly speaking, these operations basically transform a function into another function. For example, consider the quadratic function x squared. This function can be transformed into a linear form by taking its derivative, and also it can be transformed into a family of cubic polynomial functions by taking its integral. So the operations that we're going to use on this function are differentiation and integration. You can simply take the derivative of x squared, which is 2x, a linear function, and you can take the integral of x squared dx, which is a third, x cubed plus constant of integration. That's why we say that we have a family of cubic polynomials. Moreover, these two transforms or transformations possess the linearity property. It means that the transformation preserves the linear combination. Or basically, that transform linear combination to the linear combination as we present here. So the differential of alpha f of x plus beta g of x is alpha times f prime of x plus beta, the derivative of or differential of gx. This basically transforms the linear combination to linear combination. As you saw for integration, the integral of alpha f of x plus beta g of x can be written as alpha, the integral of f, plus beta, the integral of g. These are basic properties that we see in elementary calculus. In this section, we're going to examine a special type of integral transformation that we're going to call Laplace transformation. In addition to possessing the linearity property, the Laplace transform has also many interesting properties that make it very useful in solving linear initial value differential equation problems. Let's begin integral transform. If f of x and y is a function of two variables, then a definite integral of f with respect to one of the variables leads to a new function. For example, by holding y constant, we see that the integral from 1 to 2 of 2x times the second derivative of y dx is nothing but 3y squared. Similarly, a definite integral such as the integral of k of s and t multiplied by f of t dt when t ranges between a to b transforms a function like f of variable t into a function of capital F of variable s. We're particularly interested in an integral transformation, where the interval of integration is the unbounded interval 0 to infinity. If f of t is defined for positive, or in the worst case scenario, 0 t value, then, as you remember, we have the improper integral k of s and t f of t dt when t ranges between 0 to infinity. It's defined as the limit of the definite integral from 0 to b of k of st f of t, and then you take the limit as b, the upper bound goes to infinity. And as you remember, we call this improper integral. If the limit exists, then we say that the integral exists, or it is a convergent integral. We also use this in calculus when we are working with series as well. If the limit doesn't exist, then the integral doesn't exist and it is a divergent integral. The limit here will in general exist for only certain values of the variable s. So with these introductions, let us begin defining a Laplace transformation. Suppose f is a function defined for t more than equal to 0. Then the following integral 0 to infinity of e to power negative st times f of t dt that we denote by L of f of t. So please pay attention. Your f of t is repeated inside your integral. And here you have e to power negative st present multiplied by f of t. This is called the Laplace transformation of f, provided that the integral is a convergent integral. So let's take a look at a few examples. Suppose I ask you to evaluate Laplace of constant function 1. This is your constant function. L of constant function 1 is defined as the improper integral of e to power negative st times the function, which in this case, a constant function 1. So we are going back to calculus. How did we define an improper integral? The improper integral from a to t of f of t, if t is more than equals to a, is basically can be representing the improper integral from a to infinity of f of x dx, which is basically the limit of the definite integral from a to t of f of x dx as t goes to infinity, provided that this limit exists. So this can be written as the limit of the proper integral or definite integral 0 to b of e to power negative st dt as b goes to infinity. Calculating this integral should be very easy for you. You have e to power negative st divided by s as t bounded between 0 and b goes to infinity. So let us plug in b, plug in 0, and find the limit. You have the limit of negative e to power negative sb plus, when you plug in 0, you get just 1 divided by s as b goes to infinity. This guy becomes 0, so it is 1 over s. So provided that s is positive, in that case, we say that, hey, the Laplace transformation of L of 1 or just for constant function 1 is 1 over s. Again, remember that we take s to be positive. In that case, the exponent negative sb is negative. It goes on the denominator as b goes to infinity. This quantity approaches 0. And please remember that the integral diverges if s is negative. So we only impose that s is positive. The use of the limit sign becomes somewhat tedious. So we're going to adapt the notation of 0 to infinity as a shorthand form for writing the limit of the quantity as the variable ranges between 0 to b and b goes to infinity. So for example, the Laplace transformation of 1 or L of 1 is the improper integral 0 to infinity of e to power negative st times 1 dt, which in short form is negative e to power negative st divided by s, as your t ranges between 0 to infinity, which is 1 over s. And please note that you're imposing that s is positive. Otherwise, this is going to be a divergent integral. Let us take a look at another example. Now, suppose I ask you to evaluate the Laplace transform of function t. So let us go over the solution together. From the definition, The Laplace transform of t is the improper integral 0 to infinity of e to power st times the function itself, which is t. Remember that in order to calculate this integral, we need to use integration by parts. The integral of u dv is uv minus integral v du. So what's happening here? We need to select the proper u and dv. Let us take u to be t and dv to be e to power negative st dt. Now let us continue. We're going to differentiate u. The derivative of u is equal to the derivative of t. And integrate dv. So v becomes e to power negative st divided by negative s. So let us plug this into the formula, the Laplace transform of t, which is uv minus integral v du becomes u times v. But remember the boundary for t, 0 to infinity, plus v du. V is negative e to power negative st divided by du, which is dt. And you can write down 1 over s outside your integral, and two negative signs becomes positive. And calculating the integral of e to power negative st is very easy. Remember the definition of improper integral. Please note that as t goes to infinity, e to power negative st tends to 0. So for infinity, this guy is 0. What happens if I plug in 0 for my t? Obviously, I get 0 as well. So the first quantity here is nothing but 0. We just need to calculate the integral 0 to infinity of e to power negative st and multiply it by 1 over s. And this is equal to 1 over s times, as you remember, this is the definition of Laplace of 1. So you're basically multiplying 1 over s by Laplace of 1 that we calculated in previous page. It was 1 over s. So all you need to do is do the multiplication. You get 1 over s times 1 over s, which is 1 over s squared. So we just calculated the Laplace of t, which is 1 over s squared. With the same process, we just basically calculate the rest of the Laplace transformation for different types of functions using integrals.